In this video, we're going to take a look at some properties of definite integrals. So our first property is if a function f is continuous on a closed interval from a to b, then f is integrable on that closed interval, right? So when we say it's integrable, then we're saying that that integral, that value, it exists, that definite integral. The integral from a to b f of x dx, the integral from a to b of f of x with respect to x, that integral does exist. All we need to know is f is continuous on that closed interval. So that's our first property. Our second two special properties are two special definite integrals. If f is defined at x equals a, then the integral from a to a of f of x dx, that integral is 0. I think this, you could kind of make some sense. So if this is our value a, we're asking how much area is under that one value, right? And there's no width to that. It's not two-dimensional. It's just one-dimensional, right? And so we don't have this two-dimensional area. If f is integrable on a b, then this other idea is the integral from a to b of f of x with respect to x is equal to the negative of the integral from b to a of f of x with respect to x. So what happened there? Well, this we see that if we change our limits of integration, we switch them, we flip-flop them, then we pick up a negative. Right? So we pick up a negative by switching the limits of integration. But it's not going to change anything else. So that's those are two special definite integrals that we might encounter. Our next property deals with adding integrals. So here, if we have an integral from a to b, f of x dx, then that is going to be equal to an integral from a to c of f of x with respect to x plus the integral from c to b. And all that is provided, so I jumped over the if portion, but if it's integrable on those intervals, right? So as long as those integrals all exist, then this is fine. And again, I think we could convince ourselves that this is true. So if this is a and this is b, let's place c between it. C does not have to be between it, but I'm going to place c between. The integral from a to b, a from a to c, that's going to give us that area. The integral from c to b, that would be that area. And if we add those two areas together, we have the total area from a to b. And so if we're going from a to b, we can split it up and go from a to c and then go from c to b. And again, it's okay if c is outside that interval from a to b. Things will still work. If c was over here to the right of b, we would have all of this area up to c. But then when we go from c to b, that would be the negative of b to c. So you'd end up subtracting this and still be left with just the stuff in the middle. So those are some properties of definite integrals. We have more properties of definite integrals. So let's look at our next properties. If f and g are integrable on that closed interval from a to b, and k is a constant, then k times f is integrable on that same interval, and so is the sum or difference of those two functions. Right? So here, if you have the integral of k times f of x dx, then that constant you can bring out in front of the integral. And similarly, if we have two functions that are added or subtracted, then we can just add or subtract the integrals of those. So we can integrate those two functions separately and then combine them in the appropriate manner. Notice we don't have a rule for multiplication or division. That's because those don't work the way that we would want them to. Those aren't actually going to follow those ideas. All right. So in our next video, we will look at a variety of examples and think more about what are these rules, what is this definite integral. We're just going to play with them some more in some examples. So we will see you there.